try this again. Hello, everybody. Welcome back to Markov processes. Oh, wow. And my light just fell down. So it's really bright. We were talking about the Chapman-Kolmogorov equations, but there was a question last time about the sample path I was drawing at the very beginning of the last class. And I think we're finally in a position to answer it. And it sort of involves simulation. So this is just a little aside, which I think is totally worth it because some problems that we're going to do today I think are going to be clarified if you think of kind of how to generate processes. So let's go. So you should see my screen right now. Let me know if you don't. Simulation. So if you wanted to simulate an exponential distribution, hopefully you've seen that our continuous random variable, an exponential distribution with maybe a rate parameter lambda. What does that even mean to simulate from this distribution? It means you want to produce a list of numbers, and there is a PDF for this distribution. Oops. And it starts at lambda and goes down all exponentially. It is actually lambda e to the minus lambda x on positive x values. And this PDF, area under the curve, represents probability. So if you want to know the probability that, say, x is between 0 and 1, you want to find the area between 0 and 1, and you would compute it by integrating this PDF. And if you want to simulate values from this distribution, then you want some kind of algorithm that's going to produce a list of numbers. And you want to get something like 0.798823, 1.135299, etc. You get some list of numbers, and any one number alone is not going to allow you to see the distribution. But if you compute the probability you're in here, and I'm sorry, I don't have an actual, this is going to be 1 minus e to the minus lambda, and I don't know what that number is, but it's a number. The estimate of the probability of being in here is what you should see if you take your list, and hopefully it's a long list, and compute the proportion of values in there between 0 and 1. So if you have a long list, the proportion of values that you generate between 0 and 1 should be approximating the probability that's captured between 0 and 1 under the exponential PDF. So that's what it means to, simulate a random variable or simulate from a distribution. In this class, in Markov chains, we are going to use Markov chains in two ways. One is we'll have a Markov chain or process of interest, and we want to understand it better through simulation. But the second thing, which I think personally is more important, is if you want to simulate values from a crazy distribution where there's no kind of built-in way to do it in software, we're going to figure out how to create a Markov chain that is settling down to a given distribution. And that's not going to make sense actually until I get to what I was trying to explain. So I was giving you a sample path or a realization of a Markov chain, and we had time and we had the state space, and a realization is just some observations. So maybe at time 0, you're here, and then you're here. And then at time 2, you're here. That was an awful line. You're here. And maybe at this time, you're here. And so I said this was like a realization, a generalization. Like imagine flipping a coin, a fair coin, heads and tails. How are you going to know it's fair? You can flip it, but flipping it once is going to tell you nothing. It's a long run thing, and you have to generate realizations many, many times. How could you generate such a sample path? I'm going to make this actually simpler. Let's say we have only states 0, 1, 2. I guess I have 3 in my picture. You know what? I don't want to have 3. So let's just imagine that the state space is 0, 1, and 2. And we have some transition probability matrix, 0, 1, and 2, 0, 1, and 2. And we've got some probabilities like 0.5, 0.2, 0.3, totally making these up, 0.4, 0.1, 0.5, 0.7, 0.2, 0.1. So we learned last time that the probability that you go from, say, state 2 to state 1 is read out of this probability transition matrix. And so you want some sort of way to generate a path so that if you collected in this path all the time that you are at state 2, the next value is going to be state 1 with probability 0.2. And all of simulation comes down to uniform random numbers. This is not really, you don't need to leave this lecture knowing how to simulate anything. We're not doing simulation yet, but I think, again, this will help me explain something today. So I'm sorry I'm going a little fast. But perhaps you've seen the continuous uniform distribution, which is usually given over an interval, like from some number A to B. And for a continuous uniform distribution, there's going to be some PDF or curve under which area represents probability. And the continuous uniform distribution is the continuous version of equally likely. So you want the probability of being in this interval to be equivalent to the probability of being in this interval, as long as they're the same length. No matter where you move, you want to capture the same probability. And the only way to do that is to have a flat line. And so if the random variable u has that squiggly line means has the distribution. So if this has a uniform distribution on the interval from A to B, the probability density function is just this flat line. And we can write it as f of u or f of x is okay too. The height, since the width down here is b minus a, the height is going to have to be 1 over b minus a, so that the total area there, which is a rectangle, will be 1. So we get 1 over b minus a, as long as u is between a and b, and whether or not we have those endpoints really doesn't matter. And it's 0 otherwise. And if you were to simulate from this distribution, then you want some way to produce a list of values between A and B, such that in the long run, if you were to make a histogram out of those, so for this first bin, if the height of the histogram is such that the area of the bin is the proportion of times you saw numbers between A and this number in your sample. So the y-axis could be counts, right? If this is like a number A and this is A plus 0.1, sometimes the y-axis is how many values you saw in your sample. But often we put what is known as density on the y-axis, which makes it so that the area of your bar that you generate from a sample is the proportion of values you saw between those numbers. So this is where a random number generator comes in. Random number generation is going to be an algorithm that will somehow produce uniformly distributed random numbers. And most likely uniformly distributed on the interval between 0 and 1. And this is built into almost all software, certainly all mathematical and statistical software, some way to generate these numbers. And most software packages, especially if it's statistical, will have ways built in for you to generate numbers from, say, an exponential distribution. But in this class, I want to tell you how that happens. I want you to A, understand what the software is doing, and B, be able to write your own code in the case that you have some wild distribution that's not pre-programmed. So we want to know, we don't just want this black box stuff going on, but I am going to leave this as a black box. So talking about random number generators could take us quite a while. I mean, you can actually spend a semester talking about how random number generators work, but they are algorithms that are trying to produce independent numbers that appear to be uniformly distributed between 0 and 1. They're actually algorithms and they're recursive, so they're far from independent, but they kind of mimic it, which is why people call them pseudo-random numbers. So every simulation we're going to do in here is built off of the idea that you can figure out from whatever language you're using how to generate these uniform numbers. And when we have an actual programming assignment, I'll give you some hints there if you have no experience. The point of this was how to generate that sample path. And before I get there, let's just talk about a discrete RV, random variable X, that just takes on 3 values, like 1, 2, or 3, just to make this easy. 1, 2, or 3, with some given probabilities, say 0.5, 0.25, and 0.25. So if you wanted to simulate from this distribution, what you want is an algorithm that will give you output, that will give you output where you'll see like a 1, a 1, a 3, a 1, a 2, a 1, a 3, 2, 1, that will give you output. And in the long run, half of these will look like 1s, half of them will be 1s, a quarter of them will be 2s, and a quarter will be 3s. That's the goal. And assuming that you can get that uniformly distributed random number continuous on the interval from 0 to 1, here's how you would do this. Now, in most software, there is probably a function with a name like sample, where you can feed in these numbers and you can feed in these probabilities and it will do it for you. But here's what it's doing behind the scenes. So what you do is you take the unit interval between 0 and 1, and you grab a uniform number on the interval 0 to 1. So you get a realization. It spits out a number like 0.2381792. And you know that that number is equally likely to be anywhere in this interval. So the chance that it is below 0.5 is 1/2, and the chance that it's above 0.5 is 1/2. So if you get a number and it's below 0.5, you can generate X. You can say if the uniform you generate is less than or equal to, it really doesn't matter, 0.5, you can set or output X to be 1. And if your uniform, oops, I need to move this over. I really didn't want to do simulation, but this is going to, I think, really help with a particular problem today. So if it's between 0.5 and 0.75, that is an interval of length 0.25, and it will be in there 0.25 of the time, so 1/4 of the time. And so if you set your X to be 2, and then finally, otherwise set X to be 3, that's how you can generate this list over here that's going off the screen. That's one way to do it. That's a pretty organized way to do it. For your first thing here, you can say, oh, if my uniform is between 1/3 and 1/3 plus 1/2, I'll set it equal to 1. You can chop up the interval in different ways. Let me know if that doesn't make sense. And again, you're not supposed to walk away with the, oh, I'm seeing I'm still not used to, I can turn it off, but I'm still not used to Zoom reading my hand gestures. It doesn't read all of them. So I will go through this slower when we start simulation, but I wanted to talk about that sample path that I put up last time. Yes. So excuse the scroll while I go back just to grab this matrix. Go here. If I am trying to look at a sample version of the Markov chain that lives on the state space 0, 1, and 2, and it has this probability transition matrix, here is what you can do. So imagine a y-axis with a 0, 1, or 2, and then a time axis what you can do is you can start the Markov chain at time 0 at any place. Let's just say I'm going to start at 1. This is arbitrary. And you want to know where it's going to go at time 1. So you grab yourself a random number. I'm going to call it U1, a uniform 0, 1, and you grab that from your software so that it's actually an observed value and no longer a random variable. And then you say, I'm currently in state 1, so I'm going to look at the 1 row. And then if my uniform for time 1 is less than or equal to 0.4, that's how much time I want to go from 1 to 0. And in that case, I will go to 0. So you would set x1 to be 0. And if the uniform is not between 0 and 0.4, oh gosh, you can hear me, right? This never ever happens, but now it's happened twice in class. It says my Zoom has quit, but I think I'm still here. Can you see my screen? Or just let me know if you cannot see my screen. Okay, so if your uniform is between 0 and 0.4, you'll output a 1. And if it's between 0.4 and 0.5, this is 0.1 away, you could output a 2. And if it's between 0.5 and 1, you would output a 3. And that's how you'll get 1, 2, and 3 with the right probability. And all of this is based on starting here at 1, and looking at the 1 row. So to generate a sample path, you generate uniforms and you look at the corresponding row of the matrix and you go somewhere. And don't worry, I'm not gonna keep doing this more than one more time step, but now I'm at time step 2. And I'm gonna grab another uniform, like a U2 from this distribution. And to figure out where I go next, given that I'm at time 2, I'll compare that uniform to 0.7 plus 0.2, or, I'll break up the interval and I'll figure out if I'm going to 0, 1, or 2. So what the heck was all that for? I'll tell you when I get to it in class today. This is going to help me to explain a theoretical problem. Like I'm going to say, imagine generating a path. This is why this is happening. So that was a pretty big aside, but yeah, does anyone have any, I don't know if I should, I mean, you don't have to do this yet or know this yet, but does anyone want anything clarified? All right, we're going to go back to the Chapman-Kolmogorov equations. At the end of the last class, we computed, we had a simple Markov chain. I don't remember the state space or the matrix, probably took on values 0, 1, and 2. Markov people always start from 0 for some reason. And we had probabilities. What we did was we had a Markov chain, an example, and we had a matrix filled with one-step transition probabilities, and that tells us the probability of moving from one state to another in 1 unit of time. But then we tried to figure out the probability of doing that in 2 units of time, and we went through all the possible paths to get there, and then we noted that what we had appeared to be an entry from the transition matrix squared. And we want to prove that. So we've got the Chapman-Kolmogorov equations here. So recall that Pij was our notation, and that's a lowercase p for a one-step transition probability. The probability you move from state I to state j in any 1 unit of time. And then at the very end last time, we were moving up to n-step transitions. And I was calling that p sub ij and then an n in an exponent in parentheses. So I'm going to say super n, so I don't have to say to the n because it's not the nth power. This is going to be not probability. This is going to be an n-step transition probability. And so this is going to be the probability that at time n, you're in state j, given at time 0, you're in state I, but we are assuming all of our Markov chains are time homogeneous. So much so that this is the last time I'm going to write TH for time homogeneous above the equal sign, because it's just always the assumption. So if we start in state I at time K, and then we look at n units of time later, so time K plus n, this is also the probability that we've moved to state J over those n units of time. So note that, oh, check this out. This is kind of cute. So note that Pij super 0 makes sense. This is the probability you move from I to j in 0 units of time. And some of you might be saying, well, how can that be? We can't move. And that's exactly the point. With probability 1, we will be in the same place. So we get probability 1 if j is equal to I and 0 otherwise. And for those of you that have heard the words, yes, this is a Kronecker delta. If you don't know what I'm talking about, do not be concerned. Okay, so we've got this kind of already defined for 0 and 1 because our regular Pij is Pij and then this like 1, the one-step transition probability. So what are the actual Chapman-Kolmogorov equations? There's at least 2 ways they're commonly written. The probability that we go from I to j in some n plus m units of time can be written in a lot of ways, but one way that's going to be really useful is for us to stop in between. So go for the first n units or the first m units and go somewhere and then finish the path. And we can go anywhere for those first m units of time. So one way to write this down is the sum over all states k in the state space S. So I'm always using that S to denote the state space of the Markov chain. And we'll go from I to some intermediate K in M units of time, and then from K to J in the remaining N units of time. We're going to prove this, but you could sort of see that Markov property, a kind of independent transition thing. You know, the states are not independent of each other, but once you've landed somewhere, the transition to the next state is independent of where you came from. And we've got like a multiplication here of probabilities. And this has to hold for all integers n and m, 0, 1, 2 on up. And another way that it is usually, or that is commonly stated, is the probability of going from I to j in any n steps can be written as the sum over all k and s of the probability of going from I to k in some m steps. Now here m is going to be a number between 0 and n. And then we'll go from k to j in the remaining n minus m steps. And k could be anything, and that's why we are summing over all possibilities in there. So these are 2 statements of the Chapman-Kolmogorov equations, and let's prove the first one. We can prove either one, they're totally equivalent, but I kind of like the first one better. I think it's a little clumsy to only have the m between 0 and n. So I'm going to prove the first one. I'm going to start with the left-hand side, the probability of going from I to j in n plus m units of time. And there's a couple of ways we can write this. Sorry about the scroll, but it's up here, right? Of course, we have n plus m. So by time homogeneity, let's just start at time 0. Okay, so one way to write this is the probability that x at time n plus m is equal to j, given that x at time 0 is equal to I. I'm going to condition on where we are at time m. And this is one of the last times. I'm not like threatening to leave it. I think you might be sick of me writing this. So there's this intermediate step, which gets you the conditioning. And that is, we can write this as the sum of the probability that xn plus m equals j, I am going to also include where we are at time m. I'm going to say we're at some k, and I'm going to run over all possible k, which marginalizes that out. This all happens in conditional land where x0 equals I. And then again, if you sum this one out, you're left with just this part of the conditional probability. And then we can unravel the definition of conditional probability by writing this as the probability that xn plus m equals j given xm equals k times the probability that xm equals k, but all probabilities stay in the conditional land where x0 equals I. So here's what I mean about writing this again. To go from the beginning to this first line to this third line, we are conditioning on where the chain is at time m. So condition on the location of the chain at time m. And then, that's something I'm going to start eventually going directly to without that intermediate line. And we are done because, put this up here, by the Markov property, this first probability, given I know where the chain is at time m, I don't care where it was back at time 0. And so I can remove this x0 equals I by the Markov property. And once I do, I'm done. This is the sum over all k. The first probability is me going from k to j in n units of time. And our notation for that is p kj super n. And the second probability is the probability of going from I to k in m units of time. So this is, in our new notation, the probability of going from I to k in m units of time. And although they're written in the reverse order, it's just multiplication of scalars. We have proved the Chapman-Kolmogorov equations. That's what we were out to show. So super easy.
Super easy, barely an inconvenience.
If you know the definition of a Markov chain and if you are comfortable with the basic calculations for a Markov chain. And again, this multiplication here, here's where you can see the kind of idea of independent transitions. Where you go is not independent of where you are, but where you're going next is independent of how you got to where you were. So these are going to be really useful equations. More notation, I am going to let this bold double P, this was what we were using to denote a probability transition matrix. And now I'm going to put a super N in parentheses. I'm going to let this denote the matrix of n-step transition probabilities, i.e. the ijth entry is lowercase pij super n. I don't know if that looks lowercase, but that's a lowercase p. So now we have new notation for how we collect them. The ijth entry is, well, I just wrote that, but lowercase pij super n, and by the Chapman-Kolmogorov equations, this is the sum over all k in the state space of pik in m units of time times p kj in n units of time. And we could have interchanged the n and m, right? We could condition on where we are at time m or at time n. We are moving from 0 to n plus m, and we could have broken it up anywhere. But you can see now as k runs over the indices in this sum, this is running across the ith row of one of these transition matrices. This is running across the ith row of this capital P, sort of super M. the matrix filled with m-step transition probabilities. And this one is running down the jth column of capital P super N. And then this is not true. So I'm going to go back up here and fix this. The ijth entry of this big bold P super N plus M is this lowercase Pij super N plus M. And by Chapman-Kolmogorov, we can write it like the right-hand side. And these terms, as K runs over S, are running across the ith row of P to the M. And the other terms are running down the jth column of this big bold P super N. So row column multiplication, that's exactly how you multiply a matrix. The ijth entry of our new matrix comes from running across a row and a column and multiplying elements and summing them. This is telling us that the actual transition matrix for the N plus M step transitions can be gotten by matrix multiplication of the M step transition matrix and the N step transition matrix. So this is matrix multiplication. And in particular, we know other things now. So in particular, P, say 2, is P, capital P, super 1 times capital P, super 1. But both of those are just the one-step transition probability matrices, which we call P. And now I'm just multiplying two matrices. So this is the matrix P squared. This is what we saw last time in our example. The matrix filled with two-step transition probabilities is just the one-step matrix squared. And I'll just write one more line. I think you know where I'm going with this. The matrix filled with three-step transition probabilities can be written as the couple of ways, but as the matrix of two-step transition probabilities times the matrix of one-step transition probabilities. But by the line above, the matrix of two-step transition probabilities is the matrix squared. And we know that the matrix of one-step transition probabilities is the matrix to the first power. So now this is just matrix multiplication to give us the cube of the original matrix. Yeah, in general, if you want the matrix filled with n-step transition probabilities, you can just take the original matrix to the nth power. However, we do not have that Pij, the lowercase Pij super n. This is not the original Pij to the nth power because matrix multiplication doesn't work that way. The ijth entry is not the original ijth entry to the nth power. You got to put together those rows and columns. Yeah, so if on this homework assignment, I give you a matrix and then I say something like, what is the probability that x3 is 7 given x0 is 1? One way to do this is to cube the matrix. And you can do that with software or anything, you don't have to cube them by hand. And look at the 1, 7 entry, row 1 and column 7. Okay, so what we observed last time was true. We're going to use the Chapman-Kolmogorov equations a lot. Speak up at any time if you're not sure what I'm doing, but I'll usually put like a CK above an equal sign when I'm using a Chapman-Kolmogorov equation. And an MP for Markov property and a TH for time homogeneity. They're really piling up. Next up, absorbing states. Absorbing states for a Markov chain. I'm too lazy to write the whole title out. So this is a state that once you hit it, you can never leave. You get stuck there forever. It's like a sink. Big classic example of an absorbing state is the gambler's ruin problem, which we'll talk about in more detail later in the semester. But if you let like xn be your total amount of money, and you're playing some game that has rounds, round 1, round 2, round 3, and you have a certain gambling strategy. So sometimes your money goes up, sometimes it goes down. State 0 in theory is an absorbing state or should be. You shouldn't go to the ATM. You shouldn't go to the loan sharks is an absorbing state. Walk away. I mean, ideally, it's an absorbing state. You hit it and the game's over. You're going to be staying at 0. So as an example, in sort of more what we're looking at, we might have like a state space like 0, 1, and 2, and then a transition probability matrix, say 0, 1, 2. We just put like, why am I getting so sloppy? Like 1/2, 1/4, 1/4. And then for the 1 row, I'll put 0, 1, 0. Right. So that means if you're at state 1, you only go to state 1. You are stuck there. And then whatever for this one, like 1/3, 1/3, 1/3. But in this example, state 1 is absorbing. How often do you come across an absorbing state? Maybe not that often, but we're going to want to turn states into absorbing states to help us solve more complicated problems. This is a really cool trick. So what we want to do next is solve a problem by inducing an absorbing state. I think you're going to love this. Here is my example. We're going to go back to the bike station example. I'll remind you of what the matrix is. So we were following one bike as it moved between stations called A, B, and C, and we had a probability transition matrix on A, B, and C. And across the top row, it was 0.3, 0.5, and 0.2. Across the next row, it was 0.1, 0.3, and 0.6. And across the last row, it was 0.7, 0.1, and 0.2. And if any of those are actually not right, well, this is our new matrix for a different example. I think that's what we had. So I have a few questions for you. Question 1, the bike is currently at station, say, B. And I want to know, so what is the probability that it is not at station A for any of the next 3 days? So if xn is the position on day n, here's what we're trying to compute. We want to compute the probability that x3 is not A and x2 is not A and x1 is not A, given x0 is B. So the brute force way to do this, so that you can appreciate our other way to do this, would be to consider all the ways this can happen. And clearly you do not want to do this when the state space is larger and there's more time steps involved. But you can say that, like, I'll make a little table. Today, we are at station B, and then the next 3 days, we could go to maybe B, and then to B, and then to B, or B, and then to B, and then to C, or B, and then to C, and then to B. There are actually 8 places there's 8 paths we can take where we don't hit A. I want to go to C, C, C in the end. So there should be 8 outcomes there in the dot, dot, dot. I mean, a total of 8. And this is going to happen with probability. So I've got this WP for with probability. The first sample path takes you from B to B, and then from B to B, and then from B to B. So it's like, given you're at B, what's the probability you then move to B? And now given you're at B, you move to B again. And this is just multiplying B to B probabilities. So this is going to be 0.3 for the first transition, 0.3 for the next transition, and 0.3 for the final transition, because there's 3 yellow arrows there. In the next row, so we're always starting at B. In the next row, I go from B to B, and then B to B, and then B to C. So we're going to grab the B to B probability of 0.3, and then we get that again. And for the final transition, we're going from B to C, which is 0.6. And so we can list all these out. I'm just going to write the last one. Starting at B, looking at the matrix, we go from B to C with probability 0.6. And then we go from C to C with probability 0.2. And then we go from C to C again with probability 0.2. And those are all the disjoint ways this can happen. You know, you can't take one of these paths and at the same time take another path. So to compute the probability that we want, we need to compute all these and add them up. So I'm going to put a sum on the right side. It looks a little weird. And if you add these up, you should get 0.225, which is a lot of work. And again, if there's more time steps and more states, you definitely don't want to be doing it this way, this brute force approach. So here's where the absorbing states come in. Oh, by the way, another brute force approach would be for you to list out all the possible paths that do go through state A, and you'll get the rest of the probability. You'll get the 0.775. So it's a complement approach, you know, and you can compute 1 minus that probability. Okay, so before I do the better way to do this with absorbing states, I do have to fit in a little aside. Sorry about this, but kind of wouldn't have made sense for me to mention it earlier, I think. So it's just two mistakes people make with Markov chain calculations. This is not this particular example. I'm just making some states up right now. So the probability that, say, x3 is 5, given x2 is not 1, because this is the sort of thing we're about to work with, these not equals. And say x1 is 4 and x0 is 3. So consider this probability. This is not the probability that x3 equals 5, given x2 is not 1. The Markov property does not give us that, because it says where you go depends on where you are. And so I'm looking at time step 3. And the problem is I don't know where I am at time 2. I just know where I'm not. So you actually don't get this by the Markov property because you don't know exactly where you are at time 2. So a lot of people make that mistake, and I totally see why. You know, you just need that last piece of information, but you don't actually know where you are at time 2. And it is also not the probability that x3 equals 5 given x1 is 4. It is tempting to look at the history and go to the last piece of information you are given, but it's not like we don't know anything about time 2. This is actually more information. So you can't just grab the last piece of given information because you're not using this information. I don't know if that makes sense, but these are two ways people misuse the Markov property. And if you want to see what this is and what this is and what this is, you can do the calculation the same way I'm about to answer these questions. So going back to the bikes, question 1, an alternative solution. I'm going to go grab that rather than write that again. Here's what I want to compute. That's bugging me. Move you down. Here's what I want to compute, and I claim that I can use an absorbing state to do this. So what we're going to do is consider another Markov chain. I'm going to call it Y0, Y1, Y2, another Markov chain yn running according to a different probability transition matrix to a transition probability matrix. I could call this P sub y, but I'm just going to call it Q. It runs over the same state space. So I'm going to make this the same as it was for xn, except I'm going to make the state that we don't want to hit, which is A, I'm going to make that absorbing. So if A is an absorbing state, that means the probability you go from A to A is 1, and the other probabilities in the A row are 0. And then I'm going to keep the other rows the same. And they were 0.1, 0.3, copy this. So I'm going to keep the other rows the same. Let's stick this down here for a moment. I'll erase it because that's quite a mess. So 0.1, 0.3, and 0.6, 0.7, 0.1, and 0.2. This problem right here is the whole reason I talked about simulating sample paths, because if you imagine a couple of sample paths here, which is just realizations, it's just, you know, flip that coin. You have heads and tails. Run that Markov chain. You've got a sequence like B, C, A, B, C, 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 B. If you look at sample paths kind of like running in tandem with the same random input, the same uniforms that generate them. For xn, maybe you'll go from starting at B, I think that's what I was starting at here. You might then go to C, you might go back to B, stay at B, go to C, go to A, go to B, stay at B, go to C. But if you were running the yn chain, it's gonna, if you started at B, it's gonna stay in sync with that X chain. But once you hit A, it will get stuck there and it will stay there forever. So check this out. The probability we want to compute, the probability that x3 is not A and x2 is not A and x1 is not A, given that x0 is B, this is the same as the probability. I'm going to write it and then I'll talk about why. I'll try to convince you it's the same. This is the probability that y3 is not A, given y0 is B. Because the only way that y3 is not A, well, y3 will be A if and only if the X chain hit A along the way. So if y3 does equal A, that means that either x1 is A and or x2 was A and or x3 was A. But the only way to have all three of these not be A is for your Y chain to also not be A at the end, because once you observe an A in the X chain, the Y chain is going to end in A. Does that make sense? And vice versa. So if the Y chain does not end in A, that's equivalent to the X chain never having hit A along the way. So I can compute this probability as 1 minus the probability that y3 equals A, given y0 equals B. And we know how to get this. This is a 3-step transition probability for the Y chain. So we can cube the Q matrix. And so this is 1 minus the B to A entry of Q cubed, which we have notation for. Let's just use our same notation. This is 1 minus Q BA with a super 3 in parentheses. And that was so much easier than the brute force approach, or it definitely is easier when you've got a lot of time steps and a lot of states. And this quote unquote trick will work if there are several states you don't want to hit. So if you have states AB3, AB3, did it again, A, B, C, D, E, F, all the way through Z, and you want to compute some kind of probability where you never hit states A or state G or state Y, you can create a new Markov chain where you make all three of those absorbing and pull the same kind of trick. So let's continue with the bike chain, and I have a second question for you. I'm going to call it Q2. Given the bike is at station B on Monday, and given that it was not at A on, say, Tuesday, Wednesday, or Thursday, I want the probability that it is at B on Friday. So also given that it was not at A on Tuesday, Wednesday, or Thursday, what is the probability it is at B on Friday? Similar but different to the problem we just did. So if we look at Monday, Tuesday, Wednesday, Thursday, and Friday, and maybe label this time 0, 1, 2, 3, and 4, then we're given this is B, and we want the probability that this is B. And we're given that it is not A in between, but we don't know the value. So it looks really similar to what we just did. It's just that the not equal sign is on the right side of the conditional line. So here's what we want to compute. We want the probability that X at time 4 is B, given X at time 3 is not A, and X at time 2 is not A, X at time 1 is not A, and X at time 0 is B. That's, half of the problem right there, trying to translate it from the words to the stochastic process. So I'll let you look at that for a second, make sure everyone's clear on the problem we're trying to solve. And let's do it. This conditional probability, I am going to approach it like a conditional probability and write this as the big fat intersection. So X4 equals B, X3 is not A, X2 is not A. So this is just the definition of the conditional probability. X1 is not A and X0 is B over the probability of all of the things after the conditional line. Well, I can't figure this out from the given transition probability matrix. I don't, it only gives us conditional probabilities. So I am going to rewrite this. I'm going to do that unravel. So right now I'm going to use the idea that the probability of A intersect B, this is not the stations, this is just a generic sort of event, A and B, is the probability of A given B times the probability of B. And I'm going to do that, and I'm going to let all of this stuff except the last guy be the event A, and I'm going to let this be the event B. So I'm going to write the numerator as the probability that X4 is B and X3 is not A, X2 is not A, X1 is not A, given X0 is B times the probability that X0 is B. That's just the numerator. And this looks like trouble because I'm going to need the probability that X0 is B, and I don't have an initial distribution here. But if we do the same thing for the denominator and write this as the probability that X3 is not A, X2 is not A, X1 is not A, given X0 is B times the probability that, X0 is B, we get cancellation and we don't need that initial probability, which is super Convenient. And now we can do the Y chain trick. So this is the same thing. Let's just look at the numerator. Given
B on Monday.
information, it's okay. But I can't say that this alone is one, because this is no longer like a given scenario. This is like, oh yeah, I've observed it B, but this is a separate question. What is the probability we start at B? Yeah, so in the, I'm going to stop saying, this is the last time I'm going to say it. You got to let me know. I just getting. Okay, so now hopefully you can see my screen. Let me know if you can't. But on top, in terms of the Y chain, this is the same thing as the probability that Y4 is B, given that Y0 is B. Because if the Y chain started at B and ended at B at time 4, I know for sure that the X chain did not pass through A, because if it did pass through A, then the Y chain would pass through A, and the Y4 chain would definitely be at A at time 4. So this already includes all of this information. For the denominator, if the X3 chain, or if the X chain, sorry, the X chain never went through A, that's the same thing as saying the Y chain at time 3 is not A. And given that we start the Y chain at B. And then if the Y3 chain is not A, that tells me that not only is X3 not A, but that X2 and X1 were not A. And so it's equivalent. Yeah, so on that not equals probability, we can handle in two ways. One is the complement way, which I think is easiest. So this is 1 minus the probability. I don't know why I'm suddenly writing huge, that it's A, given Y0 is B. And then these can be gotten from the Q matrix. So the numerator is this lowercase q from B to B in 4 time steps. And the denominator is 1 minus q from B to A in 3 time steps. But the other way I could have done this denominator here is if it's not A at time 3, then it's either B or C. So I could have written this as the probability that Y3 is B, given Y0 is B, plus the probability that Y3 is C, given Y0 is B. So the whole denominator could be QBB in 3 steps plus QBC in 3 steps. It's slick, right? I know. Yes, there is a problem, but we are going to get to an example like that and see what to do in that case. So yeah, you wouldn't be able to do it quite like this. But good observation. We will get there. I just want to do a question 3 while we're in this and milk this example for all it's worth. I want to find the probability that X4 is equal to whatever we had. X4 is equal to B, given X4 does not equal A. Now we didn't have that piece of information before. We only had X3 is not equal to A. X2 does not equal A. X1 does not equal A, and X0 is B. So this is new. And if you were, on an exam or something, or on a homework problem. So remember, question 2 was this. Let me just copy and paste this and not rewrite this. Was this. So we're going to compute the probability in question 3. But my question is, like, intuitively, do you expect this probability to be larger or smaller than this probability? I'm not expecting you to speak up. I'm just pausing so you could think about it for a second. Of course, please speak up. But yeah, it is larger. This is going to be larger. Thank you. Because we want to know the probability the bike is at station B on Friday or on the 4th day. And in this case up here, we already know it's not at A, which makes B or C more likely. So I expect this to be, this is awful for note taking, but this is larger or should be larger than this, this line down here. Just because, yeah, we're figuring out the probability we're at station B on Friday. And in the case at the top of the board, we've already ruled out something for Friday. Yeah, so intuition is good sometimes, but let's figure out how to do this. I would start this off the same way. I know the copy and paste, it really sucks for you taking notes. I try not to do it too much, but I'm going to run out of time here. So this is what I want to solve. I would write this using the definition of conditional probability. I'm going to skip one line, which is all of this intersected over the probability of all of this. I would then rewrite those by unraveling the definition and make them both the numerator and denominator into conditional probabilities given x0 equals b times the probability that x0 equals b. But then it's going to cancel from the numerator and denominator. So I claim this is the same thing as the probability x4 is b and x4 is not a, and x3 is not a, x2 is not a, x1 is not a, given x0 is b, over the probability that x4 is not a, x3 is not a. So please take some time to make sure you can reason your way through this. And let me know if you can't, either in office hours or we can talk about it at the beginning of next class, but it's the same exact trick. So what's different about this than our last example? We have this and we have this, and those weren't in there before. And in the numerator, it's just kind of redundant information because this is like, this is like, I'm going to roll a fair 6-sided die. What is the probability that I get a 4 and I get an even number? That's redundant. That's just the probability I get a 4 because that's already even. And so in this case, if I want the event that x4 is b, that already includes x4 is not equal to a. So like this is kind of gone because it's redundant. And so maybe in the next line, I would rewrite that and remove it to make it neat, but I don't want to rewrite, you don't want to see me rewrite that whole thing. So now I'm starting at B and I'm going to be in 4 steps, not 3 steps. And I did not go through A. And the way the Y chain does that is if the Y chain in 4 steps ends at B, given the Y chain started at B, the only way that can happen is, the X chain ends at B and never goes through A. Because again, if x3 or x2 or x1 was A, then y3 or y2 or y1 would be A, and that would force y4 to be A because it would be forever stuck there. And in the denominator, this is the probability that y4 is not A, given x0 is B. Because if y4 is not A, then x4 is definitely not A because they were like running in tandem if you think of generating them with uniforms. But also y4 would be A if x1 was A. It would be stuck there. So y4 not being A this should be a not equals. Implies that, x1 was not A and x2 was not A. And now this is very similar to what we did before. I can write this as the probability that y4 is B, given y0 is B, over 1 minus the probability. Y4 is A, given this should be a Y. Y0 is B. And this is the Q matrix because it's Y. I'm going from B to B in 4 time steps. And then down here, I have 1 minus the Q matrix probability of going from B to A in 4 time steps. So I am out of time. I can stick around for a few minutes. If anyone wants me to clarify, scroll back, show something else. But otherwise, yeah, I can do that, Sam. I will put these slides. I could put the slides on Canvas, but I don't have time to clean them up. So sometimes they're going to have arrows all over them, and that's not going to make sense, but I'll put them up. So I will see you next time on Markov processes. Thank you.